In this lecture, we look at the Doppler effect, or what happens when the sources and observers are moving around. What is the frequency of the sound measured if the observer and/or the source is moving? If the source and observer are stationary, and the point source produces a sound wave, then we can figure out what frequency the ear hears fairly simply. We count the number of waves that pass an ear in a certain amount of time. That's the velocity of the wave times the time divided by the wavelength, again divided by the time it takes. So the frequency is just the velocity divided by the wavelength, which we found before. Now let's look at a stationary source and a moving observer. So you might notice that the ear is moving in as the sound wave comes out. So as it moves in, it actually crosses more crests of the wave than it would have if it was sitting still. So this Doppler frequency is again still the number of crests passed in a certain amount of time, but the number is slightly different because now it's the velocity of the wave times the time we measured, plus the velocity of the observer times the time involved, divided by the wavelength, again everything divided by the time. If we rearrange that, we see that the time drops out, and we have that it's equal to the frequency times the quantity of 1 plus the observational velocity divided by v, or we can rewrite this again as to it's the frequency of the sound times v plus the observed of the observer divided by v of the wave. So that the frequency in this case, since the will be higher because of the ear moves in. It sees more crests in a certain amount of time. If the observer was moving away instead, so the ear was moving in the other direction, then the Doppler frequency would be equal to the frequency of the sound times the velocity of the wave minus the observer's velocity divided by v. This is less than 1, so the frequency is lower. Okay, now let's look at a moving source and a stationary observer. So the ear is fixed and the source moves. One thing you might notice is that the circles, though they're still circles, are shifted over because they are emitted at different times as the source moves, so that the crests are closer together on the ear side and farther apart on the side away from the ear. So what you should be expecting is that the frequency of the sound wave to the ear should be higher due to the Doppler effect in the case where the moving source moves toward the ear. Let's see how this works out. So the Doppler frequency is still the number of crests that pass in a certain time, but now the number of crests is given by the velocity times this time, but divided by a different wavelength because the wavelength is changed by the moving source. So the Doppler frequency is this v divided by this different wavelength, a different spacing between crests. This different spacing between crests, lambda prime, is equal to the velocity times the period of the sound wave minus the velocity of the source times the sound wave, times the period of the sound wave. The period is equal to 1 over f, so we can get back to the frequency this way, plugging it in. And f Doppler then, if we rearrange a bit, is equal to the velocity divided by the quantity of the velocity divided by the frequency minus the velocity of the source divided by the frequency. And rearranging yet again, we have the f Doppler is equal to the frequency of the sound wave times the quantity of the velocity of the sound wave divided by the velocity minus the velocity of the source. Now the quantity in brackets is going to be greater than 1 because you're reducing the velocity by the velocity of the source, so that as we expected, the f Doppler when the source is moving toward the observer is a higher frequency. If the source was moving away, then we'd have a different sign on the bottom. So that the v would be v plus vs, and that would give us a reduction in the frequency or a greater wavelength, as you can see on the left-hand side away from the ear. If both were moving, we can combine our two results, and then F Doppler is equal to F equals V plus or minus V observer, and divided by V minus or plus Vs. And these plus or minuses, the top ones indicate that the observer and source are moving towards each other, and the minus indicate that there would be the bottom ones indicate that they're moving away from each other. Let's look at an example. If a jet comes roaring to you towards you at 1,000 kilometers per hour, and its engine is producing 1,000 hertz whine, what is the frequency you hear as it approaches you? So there you are, and there's the jet plane whipping by. Now let's figure out what the frequency would be that you hear as it approaches you. F Doppler is equal to the frequency of the sound times this quantity, which we just talked about before, these V plus or minus the observer divided by V minus or plus the velocity of the source. Well, the frequency of the sound is 1,000 hertz. The top part is just 343 meters per second, the velocity of the sound wave, plus the observer is not moving, so it's 0 meters per second. So within the bottom, the source is moving, so we have the speed of sound, 343 meters per second, minus 278 meters per second is in meters per second. So if we go ahead and do the arithmetic, we find out that F Doppler, as it moves toward you, is shifted up to 5,280 hertz, so a much higher whine as it approaches you than what the pilot is hearing when he's in the plane. What is the frequency you hear as it flies away from you? Well, then we have to use the bottom parts of the plus or minus and plus. So we have 1,000 hertz. The top stays the same because it's 0 meters per second. But now we use the plus on the bottom. So it's 343 plus 278. So the answer comes out to be smaller, or 552 hertz. So it shifts down by about a factor of 2 from the 1,000 hertz the pilot hears. Now imagine you're in a jet and you fly past another jet. So you do that sort of passing. What is the frequency you hear as you fly away from each other? Well, then we have to use the bottom parts of the formula. So we have V minus the V observer divided by V plus the V of the source. So it's 1,000 hertz times 343 meters per second minus 278 divided by 343 plus 278. And the answer is 105 hertz. So the sound is shifted down by almost a factor of 10 as you fly away from each other in the two airplanes.